So welcome back. We'll take a look at complex zeros now involved with polynomial functions. Let me give you an example for just a sec before we start. Like, let's say you have x squared plus 4. It's a quadratic. It does not hit the x-axis, right? It obviously doesn't have any x-intercepts that are real zeros. It doesn't have any real zeros. But what if you were to find the zeros? By letting y be equal to 0, and you subtract 4 from both sides, square root, so you got, and you can take the square root of negative 4. Remember, the square root of negative 1 is I, and the square root of 4 is 2, so this is plus or minus 2i. So 2i and negative 2i are actually the zeros. They're complex or imaginary zeros, but they are zeros. They're just not real zeros. In other words, they don't cross the x-axis. It's above the x-axis. So complex zeros come in pairs. 2i is a 0, so is negative 2i. So 7 plus 3i is a 0. If a plus bi is a 0, then a minus bi is a 0. So 7 plus 3i is a 0. The other one would be 7 minus 3i. They come in pairs. If a 6th degree polynomial has complex zeros I, 3 minus 2i, and negative 2 plus i, what must the other zeros be? And this is a 6th degree, so there should be 6 of them. Well, they come in pairs. If I is a 0, in other words, 0 plus I is the same thing, then 0 minus I would be the other 0, so negative I. It tells us that 3 minus 2i is a 0. So the other one, they come in pairs. The conjugate, 3 plus 2i, you change the sign between them. If negative 2 plus I is the given 0, then the other one must be negative 2 minus I. And there's all 6 zeros for a 6th degree polynomial. And they're all complex or imaginary zeros, so none of them are on the actual visual for the polynomial. They're not on the Cartesian coordinate system, in other words. All right, how about if we were to form a 4th degree polynomial with real coefficients with a 0 of 3. So here's our zeros. It has a 0 of 3 with multiplicity 2. So there's 2 of those. And a 0 of 5i. Well, if 5i is a 0, in other words, 0 plus 5i. If 5i is a 0, then the other one is negative 5i. And there's all 4 of them because we're supposed to form a 4th degree polynomial. So let's go ahead and create the polynomial from the zeros. We don't know the leading coefficient on this, so we're just going to call it a. But we know 3 is a 0, so x minus 3 is a factor. We know it's with multiplicity 2, so there's 2 of those 3's, so x minus 3 is the next 0. And then the next one is the 5i, so x minus the 5i, and then negative 5i, x minus the negative 5i. So we've got a, and I'm going to go ahead and multiply the x minus 3. So I get x squared minus 3x minus 3x, negative 3 times negative 3, 9. And then I'm going to go ahead and multiply this x minus 5i, let me write it, x minus 5i, and this x plus 5i. I'm going to multiply those two and see what we get. So I got x times x, I got x squared plus 5xi minus the 5xi, and negative 5 times negative 5 is a positive 25. I times I is I squared. Now, if you guys remember I is the square root of negative 1, but I squared is negative 1, right? It'll undo the radical there. So I got to replace I squared with negative 1. So what we have is x squared, 5xi minus 5xi, those are like terms that cancel. Opposite signs, and then plus 25 times that negative 1, because that's I squared. And now we go ahead and we take, and we FOIL this out. So I'm going to take the x squared through to each of those. So I have x to the 4th minus 25x squared I'm going to take the minus 6x to each of those. So minus 6x cubed was 25 times 6. 150 minus 150x. And then I got to take the 9 through to each of those. So 9x squared was 25 times 9. 225 minus 225. 9 times, oh my gosh, you guys, I'm sorry. Negative 25. I missed my sign right here. Oh, I'm sorry. Negative 5 times positive 5 is a negative 25 times that I squared, which is negative 1. I'll make that a positive. Sorry about that. Ugh. So that'll be positive. It'll be positive. Yeah, that'll be a negative. And then that'll be a positive. There we go. 25 minus, oops, I got 5x squared, combining it with the wrong one here, plus 9, there we go, 34x squared. And then I've got the minus 150x. And then I got the plus 225. Good grief, I made a mess of that, didn't I? So there's our polynomial function. We just don't know the a, and that's fine. They didn't give us any other information on that, so that's where we leave it. There's our function. A could be 1, a could be negative 1, but it does have all those zeros that we described. All right, how about this one? This polynomial is a third degree, and it only tells us that one of the zeros, they only give us one of them, negative 5i. Well, if negative 5i, in other words, 0 minus 5i is a 0, then we know 0 plus 5i. So positive 5i is also a 0. Now, this is a third degree, right? So there should be 3 of them. But this is enough information for us to kind of break this down. So here's our original function. And they're telling us that x minus negative 5i must be a factor, and x minus the positive 5i is the other factor. We just don't know the other one. All right, there's got to be 3 factors, 3 linear factors, because it's a third degree, because it's got 3 zeros. Well, this is helpful because we have x plus 5i, we have x minus 5i, we just don't know the third one. I'm going to go ahead and multiply these two, and I get x squared minus 5xi plus 5xi minus 25i squared. Again, we don't know the third one there. But those cancel, and so I have x squared minus 25 times negative 1. I squared is negative 1. So x squared plus 25. And now I just got to find that third one, right? So what I'm going to do is I'm going to go ahead and go to the side and do division, long division, to find that other factor. So I'm kind of running out of room here. Let me go over here. X to the third plus 3x squared plus 25x plus 75 divided by this x squared plus 25. I'm going to write it as x squared plus 0x plus 25. And I go ahead and I multiply this. So x times x squared, x to the third. Go ahead and change those signs. That'll be a 0x, that'll be a 75. Next time will be 3. And go ahead and change those signs. And that's gone, that's gone, that's gone. So there's no remainder. So there's the x plus 3. Right, I took this one, divided by the x squared plus 25, I get x plus 3. So what's our other 0? Well, we already know x squared plus 25 gives us, that gives us the, when I take the 25 to the other side, I square root. That gives us the plus or minus 5i, but there's our other one. We just found it. -3. That's the other 0 we were looking for, right? So just to recap, we took the given 0, -5i. They come in pairs. Complex zeros come in pairs. So if -5i is a 0, so is 5i. And then they're both factors, so we set them up as x minus and x minus, multiply them together, did the division to find that remaining 0, the remaining factor, which will give us the other 0. Given this situation, we got f of -5 is 0. Find the complex zeros of this function. Well, they give us one of the zeros. It's -5. Well, there's 2 more, right? So here's the function. F of x is x cubed plus 13x squared plus 57x plus 85. And they already tell us f of -5 equals 0. So that's one of the zeros, one of the x-intercepts. So if -5 is a 0, x minus -5 is a factor. And let's go ahead and figure out the rest of it. And I can use, this is of the form x minus c. So I can go ahead and use synthetic division. -5 would be my c. And I put 1, 13, 57, and 85. And I know this remainder's got to be 0. So let's go ahead and check it. 1 times -5, -5. 13 minus 5, 8. -40, 17 times 5. Making sure that's okay. That is 85. So let's go ahead and put those in. So it'll be 1 degree less. 1x squared, 8x plus 17. Now if you notice, that does not factor straight up. Let me erase this for a minute. So we've got x plus 5, and we've got x squared plus 8x plus 17. So what are all the zeros? Well, we already know -5 is one of them. Now we got to solve this. Well, if ax squared plus bx plus c equals 0, then the old quadratic song pops into your head. X equals -b plus or minus square root of b squared minus 4ac all over 2a. And I hope you are a much better singer than me. Our b here is 8. 8 squared minus 4 times 1 is our a. 17 is our c. All over 2 times our a, which is 1. So we got -8 plus or minus a square root of 64. What's 17 times 4? 68. All over 2. So we got square root of -4 all over 2. So we got -8 plus or minus 2i all over 2. Those both go into 2, so -4 plus or minus i. So there's our zeros, -4 plus or minus i, and -5. So 1 and 2 and 3, -4 plus i, -4 minus i. 3 zeros for a third degree. Okay. All right, let's go ahead and finish off this last one here. Given a fourth degree, find the complex zeros of the function f. Well, the nice thing about this is quadratic in form, so it'll actually factor for you nicely. It's kind of like factoring x squared plus 362x plus 361. So you'd have x squared and x squared. And then in this case, it'll be +1 plus 361. If you notice, if you multiply that back, you get x to the 4th plus 361x squared plus a 1x squared plus 361, which is what we started with. X to the 4th plus 362x squared plus 361. Okay. Now, notice from here, I can find the zeros. Neither of these factor. Set equals 0. Take the first one, set equals 0. Take the next one, set equals 0, and let's solve it. Subtract 1, square root, plus or minus I. Go ahead over here, do the same approach. Square root. So this is, let me write it this way. That's -1 times 361. Well, 361 is 19 times 19. So here's the I, plus or minus 19I. So there's all four of them. I, negative I, 19I, negative 19I. And we can write this. It also asks us, go ahead and write it in factored form. So you got to take, in factored form, you got to take each 0. So you have x minus I, x minus the negative I, x minus the 19I, and x minus the negative 19I. And there it is as a product of linear factors. And there's our function in factored form with those zeros at least. Okay. All right, that's it for complex zeros of polynomial functions. Thanks so much for watching. See you next time.